Okay, I'm going to take up a few problems here today from the normal force and friction questions. Keep the questions coming. I'll make little videos anytime you guys have ones you want me to take up for the next couple of days. I'm targeting Friday for my return. Let's just make sure my writing tool is going to work. Ooh, I have it on highlighter. That's no good. So let's go here. And let's go with some red. Yeah, that'll work. Just want to make it a little bit finer, I think. Maybe like that. Yeah, that'll do the trick. So I've got a few questions highlighted, and then I have a couple of my own I might want to go back and do as well. So the first question I want to do is 39, which it says for problem 36. So I'll have to go back and look at that. Calculate the force of friction, the weight of the magnet, the acceleration of the magnet. So the force of friction acting on the magnet will be equal to the coefficient, which is right here, 0.3 times the normal force. So let's go back and look at problem 36, which I have on screen now. It says a 20-gram fridge magnet's being held onto the fridge by 0.9 newtons of force. So I'm actually going to just draw this off to the side for you. And give me some space here. So this is like that that example I did with the chalk brush, which I know was like 2 weeks ago now. But there's the fridge, there's the magnet. So if the magnetic force is 0.9 newtons in, then the fridge has to hold it out with the same 0.9 newtons. So that will be the normal force. But if you already did 36, then you already knew that. So if the normal force is 0.9 newtons, then it's pretty easy. We just go 0.3 times 0.9 newtons. And I do have a calculator today, but it's pretty suspect. But I should be able to type something in as simple as this. So I get 0.27 newtons for the force of friction acting on the magnet. The weight of the magnet, weight, remember, means force of gravity, so it's Fg equals mg. I'm just going to double check the mass, which is 20 grams or 0.020 kilograms times 9.81. So I go 0.02 times 9.81. Oof. This calculator is rough. And I get 0.20 newtons. I rounded that. So that's A and B. And then C wants the acceleration. I'm going to draw a diagram for that. So again, I'm going to go off to the side. And I'm actually going to go right to my old diagram here. So the downward force, I think I just calculated it was going to be gravity, which is 0.2 newtons. Is that right? Let's go back and look. 0.2 for gravity, 0.27 for friction. Okay. And then my upward force is a max of 0.27 newtons. And using the methods that I showed you the last time I saw you, you would say, okay, so this fridge magnet's going to accelerate up. Why is it going to accelerate up? Because it's got more force up than it has down. But remember, that's a force of friction. The force of friction can't accelerate the object up. So I'm going to actually peek at the answers here, but I'm going to assume that the acceleration is equal to 0. Because anytime the frictional force is greater than the other force trying to push it forward or pull it down, then it's just not going to move at all. So that's the explanation there. It's just that friction's too big for gravity to overcome here. They don't actually have to be equal, but it is a bit of a confusing dynamics problem because you're thinking, well, that's an unbalanced force. It should accelerate up. But you guys hopefully know from common sense that if you put a strong fridge magnet on the fridge, it does not accelerate up no matter how much friction it has. So I'm just going to double check that I didn't miss something. And then there it is, 30 in number 39, 0.27 newtons, zero point 0.2 newtons, and it will not move. And that's the reason that it will not move. So moving on to 41, it says an ox exerts a force of 7,100 newtons in the horizontal direction without slipping. That's key. And that's why some people do struggle with this. Well, what do you mean by not slipping? That means it's not going to move. It's not going to accelerate. All right. And the ox has a weight of 8,000 newtons. So not accelerating means that all the forces are going to be balanced. So let me show you what I mean by that. I'm going to draw the ox like this, and I'm going to say it has a weight of, oh man, I need a better memory, 8,000 newtons and 7,100. So it has 8,000 newtons of weight. That means the force of gravity, which means the normal force in this case is also going to be 8,000 newtons. And it says it exerts a force of 7,100 newtons without slipping, which means the force of friction is what? Of course, you guessed it, also 7,100 newtons, because the forces all have to be balanced here for it to not slip, or at least that's what they're going for there. So the question says, what's the coefficient of friction? That's force of friction divided by the normal force. So friction, 7,100 newtons, weight, 8,000 newtons, or sorry, normal force is 8,000 newtons. And I just have to type that in, and I'm going to give this calculator another try. It was successful the first time, so let's see what happens the second time. And I got 0.89, 0.89 for the coefficient of friction. We'll double check and make sure I didn't miss anything there. 0.89 on 41, yeah. So that's what you're doing there. Obviously, pause this video if you need it to slow down or go over anything again. Next one's 43, which says, for problem 42, your good friend watching you do all the work comes over and sits on the crate. His mass is 60 kilograms. What's going to happen? Justify using values. So to do that, I feel like I should do 42 as well. And key is moving with a constant velocity. I've done questions like this in class. So I'm just going to zoom in and do a quick little diagram here. Does it give me a mass, by the way? Yeah, 20 kilograms. So we've got 20 kgs. And that's going to give me a force of gravity just by going mass times 9.81. It's going to be like 196, I think, but I'm going to double check. 20 times 9.81 equals 196 newtons, which means there's going to be 196 newtons up. That's the normal force. And it's being pushed with 63 newtons. This is like that constant velocity question that I did with you, I feel like the day before I was gone. That means the force of friction is also going to be 63 newtons, and that's all because it's moving at a constant velocity, which means these forces have to be balanced. And it says find the coefficient of friction. So we can do that just by going mu equals friction divided by the normal force. Ooh, I can write that a little nicer, I think. Friction divided by the normal force. Frictional force is 63, normal force 196, and I get 0.32. Before I move on, I'm going to double check that answer, and that was 0.32 for 42. Yeah. Now, nobody emailed me and asked about 42. It was 43. So how are things going to change with 43? Well, it's the same problem, really. Except the answer can be confusing, because if all you're doing is changing the mass, then the thing's not going to move, because what's going to change, how heavy is how much mass does that person have? Oh, I don't know what happened there. Oh, how do I undo that? Oh, there we go. That's exactly what I want there. It's a confusing answer in a way, because Because if you don't change the 63 newtons, then all you're doing is changing the mass. And again, I just wanted to see the 60 kilograms. So now my mass in the middle is now 80 kilograms instead of 20, which means that my force of friction is going to increase. I'm not even going to calculate what it is, but whatever the coefficient was before, which we calculated, but it's going to be more now, right? That's going to be bigger than, it's going to be bigger than 63 newtons forwards. You're going to have the same, no, actually, you're going to have a different value here. It'll be 80 times 9.81, and that'll be the same value for the normal force. So if this is bigger than 63, which if we calculate it, we'll find that it is, then the thing can't move or can't accelerate, let's say. Now, if it was already moving, then this unbalanced force would cause it to slow down and come to a stop eventually. But since it's not moving to begin with, or we could assume that it's not moving to begin with because it doesn't give us any sort of initial velocity or anything, then we'll say that it can't move, I guess. Actually, there's two possible answers there. I think you could say. You could say the friction's too large, so you can't move it, or if it's moving, it's going to slow down and come to a stop, just to give a little extra from what the answer says. So let's move on from that one. And there's a couple more here. So a box of mass 5.7 kilograms slides across the floor and comes to a stop. Initial speed is 10 kilometers per second. I'm going to change that, which is a V1, to meters per second right away, which is going to be 10 kilometers per hour divided by 3.6. So that's 2.8 meters per second. I have a feeling I'm going to need that. And the coefficient of friction is 0.34. Find the force of friction acting on the box. So I'm going to make the box. It's 5.7 kilograms. It's sliding along the floor with no mention of a forward force. So I think the free body diagram is just going to look like this, where we've got gravity here, which will be 5.7 kilograms times 9.81, which is 56 newtons. That means the normal force will also be 56 newtons. And of course, friction is going to be over here, and I'll just do that off to the side. Friction is equal to the coefficient of friction times the normal force, so that's going to be 0.34. Can I make this go? Yeah, 0.34 times 56 newtons. So this is just for A. I'm going to go through the whole thing. So 0.34 times 5.6 equals 19 newtons. Now I'm going to mess everything else up if I don't get that part right. So I'm just going to scroll down and make sure everything agrees here. 0.2. Number is this again? 46. All right. 46. 19 newtons looks good. What do we have next here? B, find the acceleration of the box. And I guess that can be kind of confusing because, we've got the box here. It's 5.7 kilograms. The forces that are up and down are balanced, so we don't even worry about them. So we're just worried about the horizontal forces. So we could say forwards forces minus our backwards forces, like we did before I left. But all we have is a backwards force. So I can just say negative 19 newtons, because it's backwards, is equal to mass times acceleration. Or negative 19 newtons, I'm going to give myself some space here and erase that, is equal to 5.7 kilograms times acceleration. Just do a little bit of light algebra there, and you're going to get negative 19 divided by 5.7, and I get 3.3, or negative 3.3 meters per second squared equals acceleration. I don't know if they gave me any specific directions in here. No. Let's see how they express the answer, though. I'm just curious on 46. Yeah, they even have it as negative there. Sometimes they might just say 3.3 meters per second squared backwards or something like that. And to give myself some more space here again, because there's more to this. Distance traveled before stopping. So C and D are just linear kinematics problems. So how far is it going to go? So how far does it go before stopping. So when does V2 reach 0? Where V1, I believe, was 2.8 meters per second. And what else do we know? We know the acceleration is negative 3.3 meters per second squared. So just got to choose the right equation. It's D equals V1 plus V2. No, it is not. That doesn't have acceleration in it. It's going to be equation 5. V2 squared equals V1 squared plus 2AD. So V2 is 0, and you're going to get 2.8 squared plus 2 negative 3.3 times the displacement. I guess I'll do that. So you got to move the 2.8 squared over. I'm just going to tell you what I would get for an answer, just in case it doesn't line up and I have to make a correction. Oh, where's my x squared button? I'm just going to type 2.8 times 2.8 instead of hunting for it. Then I got to divide it by bracket 2 times negative 3.3 bracket equals, and I got 1.2. Distance traveled 1.2 meters. You're going to scroll down and look for 46B, C, 1.16 it says. Well, maybe they used a couple more decimal places, or maybe I'm not sure what they did. They say 1.16. My calculator actually says 1.18. So probably rounding in the 2.8 meters per second squared or something like that is the reason for that. And then finally, D wants to know how long it took to stop. So same stuff, and you're just going time equals we don't know, and then same thing, V2 equals 0, V1 equals 2.8. I think it was 2.7 repeat for the V1. And acceleration is equal to negative 3.3 meters per second squared. I wouldn't use that 1.2 because it's a rounded value, so I'd stick to the original stuff. So arranging equation 1 to solve for t is v2 minus v1 over a, 0 minus 2.8 over negative 3.3, and it's going to come to rest in less than a second. Do I want to actually type that in? Yeah, I guess why not? Tell you what I get. I got 0.85 seconds. And again, I don't know how much, I think even the 3.3 might be rounded, so it could be off ever so slightly, but it should be pretty close. 8.3, and I got 8.5. I actually got 8.48. So again, I'm assuming that's due to rounding of this guy here, the 2.8, but I don't actually know for sure. But that's how you do 46. On a test, I probably will have a question where you have to use linear kinematics, but just one. That's just kind of overkill doing it twice. It's good practice for when you guys are working on this on your own, but it's just it's going to take too much time if I ask you in a single question to do 2 or 3 linear kinematics problems. That's not really even the main focus of what you're supposed to learn in this chapter. So let's do 47 next. And I am going to give myself a bunch of space before I do that. And then before I go beyond that, before I wrap up, 47 is the last one that was requested of me. But I want to, there's one problem from the Newton's second law stuff. It had to do with the duck and the strings and stuff. If you guys, nobody's emailed me about that question, but so if you got it on your own, congratulations. That's supposed to be kind of a tough one. And then there's another one with the duck here. Yeah, in 49. Anyway, I'll get to that in a moment. First of all, I'm going to do 47. That's the last one that was asked of me to take up today. So let's go ahead and do that. So it says, which force is required to accelerate a lawnmower of this mass to 4.5 kilometers per hour from rest in 3 seconds. So the first thing I have to do here is find the acceleration. V1 is 0. Time is 3.0 seconds. And once again, they've given me a speed or a velocity in kilometers per hour. So I have to convert that to meters per second by dividing it by 3.6. So my V2 is actually 1.25 meters per second. I'm just going to double check that calculation before I go on. So I messed that up, then it's not going to work. Looks like it's right. So I go A equals V2 minus V1 over T. It's equation 1. So that's going to be 1.25 meters per second minus 0 divided by 3 seconds. Don't get into the bad habits here. I'm just trying to take these up, but I left out the units on the top there, and you'll see me do that a couple of times just to save some space, but you're not really supposed to do that. Is that all I had to do? 1.25 divided by 3? Looks like that's all it was. So I got 0.42 meters per second squared. That's rounded, so my answer could end up being slightly off of what's listed below, but we will see. So what force is required to accelerate it to that? So let's just move over here a little bit again. So here's the thing. I need a mass for it, 12 kilograms. Okay. So it's 12 kilogram mass. So it's going to have some gravity, which is going to be 12 by 9.81. It's going to have some normal force. It's going to be equal to that force of gravity. But I don't even think I need that. Not for this part, not for A. There's an A and a B because it says there's no friction. So let's just call this like an applied force. I'll just write F applied. So then that's the only horizontal force involved if there's no friction. So when I go my forwards forces minus my backwards forces, all I have is that applied forward force equals mass times acceleration, Newton's second law. So I'm just going to shorten it to FA is equal to 12 kilograms. And we know what the acceleration is. It's 0.42 meters per second squared. So the applied force, again, I'm going to match it and make sure there's no issue with the answer. I'm going to go 12 times 0.42, and I get roughly 5 newtons. So I'm going to circle that, and I'm going to check this one out. This was 47A. 47A. Oh, that's 37. Good. I thought I was way off. 5.04 is exactly what I had on my calculator. I didn't realize we could have 3 digits there, though. I don't think we actually can. So I rounded mine to 5.0. 47B is the same problem, but then it adds friction into the mix. So I'm going back up. Now we've got a 0.8 coefficient of friction. So I'm going to actually go right beside where I solved the last part, and I'm going to draw roughly the same diagram, 12 kilograms. We're still trying to find the applied force, which I'm shortening now to FA, but now I actually do need the force of gravity. So just based on my old diagram there, 12 times 9.81, I'm going to write right here. 9.81. This calculator's a bit of a chore, and I got 118 newtons. 118 newtons down. That means the normal force in this case is going to be 118 newtons up. And we're going to be able to calculate a force of friction this time, which is going to be 0.8. I believe that's what the coefficient was, times 118 newtons. So I go 0.8 times 1. No, come on, calculator. 0.8 times 118 equals 94 newtons. So now, when I go to make my F net statement, so, Newton's second law, F net equals ma, now my forwards force minus my backwards force is the applied force forwards minus friction, which I know is 94 newtons, is equal to mass, 12 kilograms, times the acceleration, which we still want it to be 0.42 meters per second squared. So I'm going to have FA minus 94 equals whatever that is, 12 times 0.42. That's, I already had that, 5.0 newtons. I'm going to move this over algebraically, and it'll be plus 94, and it makes an applied force of 99 newtons required to accelerate it at the rate that it wants. So that is that. And I believe I already looked at the answer, and that's what it is. So you're going to have to bear with me, or you may even have to fast forward the video at this point, because I actually have to find another document. I want to download the one before it to do the duck problem. And usually I do get, obviously usually I'm in class, but I usually get asked about the duck problem. So I'm going to go down to Newton's second law, and I'm going to talk my way through this just because I like to talk to myself. And I'm going to download it. And then I'm going to put it into OneNote. All right, back to OneNote. I'm going to add a page. And I'm going to insert file printout. And I'm looking for Newton's second law. There we go. So here's the document. And the question I was looking for was 2 toy ducks. That's the ticket. So it says 2 toy ducks attached to each other by a string are being pulled by a very happy guy who just got them as a graduation present. Figure 4.31. Now I've lost the picture. I wish I had the figure 4.31 because I think that would be just a bizarre looking picture. The front duck is 5 kilograms and the back duck is 2 kilograms if the guy pulls them with a force of 10 newtons and there's no friction. It says calculate the acceleration and B, calculate the tension. So this is what I call a tension problem. All right. So, I'm going to draw a better diagram after, but just to get it straight, like, well, what's actually happening here? So we've got a 5 kilogram duck and a 2 kilogram duck attached by a string, and it's being pulled in the front by 10 newtons. That's the situation right there. I know my kilograms don't look very good. I promise I'll draw it a little nicer over here. And that's all I really need to know to find the acceleration and the tension. So I'm going to go over here and draw you a picture just a little bit better. So I've got 2, draw it a little bigger, 5, and 10 newtons. So the key to finding the acceleration is just to treat it as one big mass. So finding the acceleration is actually not that hard. Just say, okay, well, it's 7 kilograms being pulled by a total force of 10 newtons. Of course, there's some gravity and there's some normal force. But if you recall, I hadn't taught you anything really about gravity and normal force when I first gave you this handout. So we could calculate those, but they're not actually going to be required for this. All we really need is Newton's second law here, F net equals mass times acceleration. The only horizontal force is the 10 newtons forwards. So then we have 7 kilograms times acceleration, and the acceleration is going to be whatever 10 divided by 7 is. So I go 10 divided by 7, and it gives me 1.4 meters per second squared. So far you might be thinking, well, we probably could have figured that out on our own. Probably. That's A. B is a little different. B, I have to go back to separating them into the 2 and the 5. So just isolate one of those two masses. Okay, I'm going to choose to isolate the 2 kilograms, and the tension in the string is going to be what pulls that 2 kilogram mass forward. Of course, it still has gravity and it still has a normal force. But as far as Newton's second law goes, like F net equals mass times acceleration, the only thing pulling the 2 kilogram mass forward, it's not the 10 newtons, it's the tension in the string. And I should have highlighted here that I don't know what reason there is for this, but most textbooks I've used use a capital T for tension force. Whereas most other forces are given the symbol like F, A, F, G, F, F, for friction and all that stuff. So if you want to write FT for tension, that's fine with me. I don't think there's a hard rule on that, but I'm just used to writing a capital T for tension. So that's what I'm using. So tension is equal to mass times acceleration. How much mass is that tension pulling? Well, it's 2 kilograms. How much is that 2 kilogram mass accelerating? Well, it's accelerating with the entire system, which we already know is 1.4 meters per second squared. So that's going to be 2.8 newtons, just 2 times 1.4, and that's the answer. So that's how I recommend you do these. There is a way when I get back on Friday, if you want me to show you how to do it with the 5 kilogram mass, because you actually can do that as well, then I'll do that. But for now, since I want to end this video shortly, I'm going to go to the one with friction. So I'm going to go back to the other document because that question, um, which is right here, 49, that question adds some friction. So it says repeat the problem for a coefficient of friction of 0.10. So that will change things a little bit. So I'm going to make myself some space right beside it, just do some erasing. So I'm going to have essentially the same diagrams, the 5 and the 2, but I'm going to also have friction going backwards this time. Same problem, but putting some friction backwards. So here we go. So I'm again, to find the acceleration, I'm going to make it as one blob of 7 kilograms with a force of 10 newtons forwards. Now this time I am going to need the normal force and I'm going to need gravity because I need those values in order to find the force of friction. All right, so gravity is just going to be the whole thing, 7 kilograms times 9.81. So I go 7 times 9.81. Come on, 81. Here we go. 7 times 9.81. There we go. I got 69 newtons. So that means I'm going to have 69 newtons up, and then friction is equal to the coefficient of friction times the normal force. So it's just 0.1. So 0.1 times 69 is equal to 6.9. I feel like I should have been able to do that in my head, but for some reason I couldn't. Anyway, so there's my free body diagram. So now I'm going to go F net equals mass times acceleration equals 7 kilograms, just like before, times the acceleration. But now on the left side, I've got a forward force of 10 newtons, but I've also got a 6.9 Newton frictional force backwards, right? So that's going to give me what, 3.1 newtons? Just because I'm recording this, I better double check, but I feel like I should be able to do simple arithmetic in my head. 3.1. Yeah, no, it worked out. Equals 7 kilograms times acceleration. So I take that 3.1 and divide it by 7, and I get a 0.44 acceleration. Make myself some space so we don't get confused. And it is 0.44 meters per second squared. We're going to double check that because I need that acceleration to be right in 49A to move forward. They say 4.5, but mine does not round to 4.5, so I'm going to keep it just as is. Yeah. 7 divided by 3. They might have done some creative rounding. Or 3 divided by 7. Anyway, I was just trying to see what they might have done there. I didn't do a whole lot of rounding. The 69 was slightly rounded, but yeah. Anyway, I'm going to go with the 0.44. So just like I did before, now I'm going to do the problem. I'm going to separate the two masses into the 5 and 2 so that I can find the tension. So that's the new part. Everybody should have been able to do the part A to the question, to the point of me just telling you, just combine the two masses and find the acceleration, right? You guys should have been able to handle that with a little bit of thought and a little bit of talk amongst each other. But the tension part is the main reason I'm showing you guys how to do this. So it's still got my 10 newtons forwards, and it's got some friction backwards. All right, it actually has a frictional force on the 2 and the 5. So now when we isolate the 2 kilogram mass, it still has that tension force forward, gravity down, normal force up, but now it has a force of friction backward. Now don't make the mistake of thinking it's 6.9 newtons, because this is just the frictional force on the 2 kilogram mass. So what's 2 times 9.81? So 2 kilograms times 9.81 is 19.62 newtons. So I'm going to write 19.6 newtons. So this is going to be 19.6 newtons as well. And this is going to be the coefficient, which is 0.1 times the normal force, 19.6 newtons, which is 1.96 newtons. So now when I go to make my F net statement, Newton's second law for this one, mass times acceleration, it's going to be 2 times, what did I say, 0.44, 0.44 meters per second squared. And now I've got tension forward minus friction backwards, which is 1.96 newtons. So there's a tiny bit more algebra to do here. 2 times 0.44 is 0.88 newtons, and then it's going to be plus 1.96 newtons is equal to tension. So here we go. 0.88 with friction. I should have a little more tension than I had before. And I got 1.7 newtons. Just trying to think if that's actually, yeah. Maybe it's less because it's not accelerating. Yeah, it's accelerating slower than it was before. So there's a combination of things at play there. I was just wondering why I got actually a lower tension force this time. It's because it's accelerating slower. So let's see how close I was. I'm probably off by a bit. Oh, it says it's supposed to be 2.8. Am I on 49? Oh, brother. Haha. Okay. Yeah, that's why. Yes, force of gravity is not, no, it is 2 kilograms, 19.62. 19.62. So now you're going to watch me struggle to figure out what I've potentially done wrong here. Yeah, that's not right. When I add those, that's my calculator that's failed me. 0.88 plus 1.96. All right, so it was a pretty easy fix. And I got 2.8 newtons just like I had before. For some reason, I just couldn't add those two numbers correctly. So 49, yeah, they got 2.86. I had 2.84 on my calculator because who knows if they had the 6.2, which I dropped the 2. I guess there's lots of things that could have happened there. But that is a good answer. And that's doing it with the 2 kilogram mass. So if you want to go and test yourself on whether or not you can do these tension problems, just have a look at 50. And if you guys want these taken up, I will take them up for tomorrow's video. But 50 says that you're adding a third duck to the row. So instead of 2 masses, there's 3 masses. So just see if you can take what I showed you here in the last 2 problems and do that. And same with the other document. So 50 is good with 3 masses with friction. Basically, if you can do 50, you're all set. But if you want to do another one without friction, I believe there's a third mass involved somewhere here. Where is that? Yeah, number 40 is the same idea where you add another duck to the row and then it says find the acceleration and find the tensions now. So give that a shot if you haven't already. And if you still struggle with it, then I'll just remind you tomorrow's lesson is just going to be more of the same. I need, unless you guys just want me to pick questions to take up and use as examples, then I want you guys to email me during class, after class, before class, and just let me know which questions you want me to do. And that can include the review I posted on Monday, because there's some tricky ones in there for sure. And that can include also the universal gravitation questions that I posted yesterday on Tuesday. So anything you guys want me to do, I will do it. Just continue to work away. And if I'm speaking to springtime 2023 class, because I might reuse this video, but if this is spring 2023 and you're watching this, just know that I'm not going to schedule the test for like the day I get back. I really don't know how everybody's doing with this stuff. So I want to make sure I get back. And there's still a lab that I'm supposed to do. There's a lab that's actually, there's a couple of questions on that lab on the test anyways, and I don't want to cut it. So we have to do that lab before I can even schedule the test. So I think I'm going to be back on Friday. I'm going to be moving pretty slowly, but I hope to be able to drive to work and walk around a little bit and help you guys out. So we may do that lab on Friday, but I guess really what I'm telling you is we're not doing a test on Friday. All right. When I talk to you on Friday, we'll probably schedule when the test will be. And then we'll have to also lock in or come close to locking in when the midterm exam will be. But it's definitely not going to be Friday. At the very earliest, if you guys are up for it, it'll be Monday. If you guys aren't up for it, then probably it'll be Tuesday for that test. Okay, I guess that's pretty much all for now. I'm just going to go ahead and stop the recording. I am feeling a little better, not just laying down and sleeping as much. So I will. I'll respond to your emails, and I'm going to make another video for tomorrow. So keep your questions coming. Please email me.